Cool. Yeah. So Uddipan and I decided to present together because we were both working on looking at phase-space snails. We thought instead of giving you the introduction twice, we would just give it once and then launch into the separate things we were looking at. So yeah, huge thank you to all of our mentors to start out with. So Martin, Elena, Catherine, Adrian, and Jason. That was great. You guys were super helpful. Cool. So just to begin with, so snails, spirals. So the dynamic students, we talked about this a little bit at the beginning of the program, but just to kind of go back and review, why is this something we're even interested in looking at? So both Uddipan and I are looking more at analytic calculations or in simulations, but we initially got excited about this in the field because we actually find it in the data. So these spirals in ZVZ were initially identified in Gaia. They've also been measured in action angle space, and this is evidence of a recent perturbation in the solar neighborhood. So right now we think most likely this is caused by Sagittarius passing through the disk, which is the most recent major interaction that the disk has experienced. Cool. So since then, people have looked at reproducing these spirals in simulations. So recently, Jason ran a series of self-consistent 10 to the 9 particle simulations of analog of a Milky Way Sagittarius merger. And here you can see just for a short clip in time, you see strong formation of these spirals across the disk, both the formation of n=1 and n=2 spiral modes. So n=1, that's just going to be a one-armed spiral, and n=2, you're going to see a two-armed spiral. So briefly, again, this was also talked about earlier on, but just a reminder of kind of the broad picture of how we think these spirals form. So you get initial density perturbation in action space, and then as that perturbation starts to wind up, you're going to get faster winding in the center, and the tails are going to trail. And so as this winds up, you're going to end up seeing this nice spiral pattern. That spiral pattern will eventually dissipate. So there are kind of two effects here. One, as the winding gets tighter and tighter, we will at some point no longer be able to recover it in like ZVZ or in JZ, theta Z. But you can also get fading due to random motions in other directions. You can also see that here, that the spiral slowly starts to fade as it winds. And both of those effects are interesting, and both those effects are things both Uddipan and I will be talking about.
Hi, everyone. So I'm going to talk about the perturbation theory, how to get snails by perturbing a disk. So first, to give you a brief picture of what kind of physical system we are looking at. So there you can see sort of a schematic of a disk, what we are doing. So we are doing a local theory here. So we are looking at a certain guiding radius and a local patch of stars about that guiding radius. And then we are projecting out that patch into a 2D space. So we are interested in the motion of this perturbation or the wave in the radial direction and in the vertical direction. So there's going to be three kinds of motion. So the stars are going to move along the azimuthal direction, the radial direction, and the vertical direction. But for simplicity, we are forgetting about the shearing of the perturbation in the azimuthal direction and just looking at the propagation in the along the radius, and also the motion of the stars vertically, that is perpendicular to the plane. So our model is effectively a 2D model. And in this case, we assume that the unperturbed disk is just an isothermal disk with a vertical density profile that is along the z-axis, but it is uniform along both x and y, where x is the radial direction. So the density and the potential are given by these expressions. The density goes 6 square, which is basically, it decays with larger distance from the plane. And the potential is given by this expression, which boils down to a simple harmonic oscillator close to the plane of the disk. And the corresponding distribution function is given by the Maxwellian. It is Gaussian in the velocities along the plane, and it goes as exponential of minus the energy in the vertical direction. So that's the picture, basically the unperturbed disk that we are now going to perturb with some external perturbation and study the dynamics. So first, I would like to give you a brief review of how we do the dynamics of such a system. So as Juan was talking about, that we have this collisionless Boltzmann equation, which we use to model these collisionless systems, for example, a stellar disk that we're looking at here. And that basically what that boils down to saying is that you have a distribution function that is the phase space density, how many stars there are in each cell in the phase space. And if you sit on that patch of stars, if you move along with those stars, then you basically do not see that the density is changing with time. So you have an invariance of the phase space density under the Hamiltonian dynamics of the stars. So that's what is said by the collisionless Boltzmann equation, that your local phase space density doesn't change as you move with the patch of stars. And that can be written in that yellow equation, a yellow shaded equation, which is basically tells you how. So now basically you stand at a particular point in the phase space and you look at how does the distribution function change as function of time at a particular space that is given by del f del t plus the Poisson bracket of the f with Hamiltonian that is equal to 0. The Poisson bracket is given by that expression. It depends on the on the conjugate variables, the position and momenta. So this equation is like a conservation equation. It is similar to the continuity equation in a fluid, which is basically a conservation of mass. In this case, it's the conservation of the phase space distribution function of density. So we usually use this equation to model the dynamics of collisionless systems. If the distribution, if we are looking at an unperturbed or a steady state system, then del f del t is just 0, and you just have the Poisson bracket of f and h is equal to 0, which simply means that your f is now just a function of the Hamiltonian and therefore the function of the action. So that's the Jeans theorem. So your f is a function of h, and so that's basically this equation here. So now, but that is only in the steady state if you don't have any perturbation. But now what we do is that we introduce a perturbation, an external perturbation, phi p, which is time dependent in the general case. So your Hamiltonian can be written as the unperturbed Hamiltonian plus the perturbation term. And we are ignoring the self-gravity due to the perturbation in the distribution function itself, just to keep things simple. If we assume now that this perturbation is weak, and therefore we can do linear perturbation theory, then we can assume that the distribution function is also being perturbed and can be written as the sum of the unperturbed plus the perturbation term, F1. So now using this, in that equation, we get the linearized form of the collisionless Boltzmann equation, which simply states how does the perturbation of the distribution function change as a function of time, given that you specify a perturbation in the potential. So we are going to use that, that linearized CBE to come up with an expression for F1. Now, as you see, that's a partial differential equation. It's hard to solve. And therefore, we do this trick of going to the Fourier space, and we expand the perturber potential and F1 both as a Fourier series in the vertical angle, theta z, and also in x, that is the horizontal direction. So now, using that Fourier series expansion, we can get this pretty horrible looking expression for F1, the NK mode of F1. So we are doing this Fourier mode analysis. But I am going to draw your attention to some terms which will give you some sort of insight, hopefully. The term in the blue, that is the perturber potential, that is forcing the perturbation in the distribution function. And we are going to have to integrate that over time once you specify the time dependence of the perturber potential. But the term that is the most important, I think, is the term shown in red, which is a phase mixing term, because it is an oscillating term, so it goes as e to the I sum omega z times t. So that's where basically the spiral winding comes from, because your distribution function, or rather the stars are oscillating at their vertical frequency in the vertical direction, and the horizontal frequency is given by the kvx, where vx is the velocity and k is the wave number. And there is this other term which is proportional to the gradient of the unperturbed distribution function. So all these different terms, basically now we need to provide the time dependence of the potential to get F1. So for the simplest case, we choose a delta potential. That is, you just hit the disk once, you give an impulsive kick and see what that does to the perturbation. And so here there are two effects that Elise was talking about, that you have the vertical winding, which goes as theta z minus omega zt, and you have the fading of the perturbation as well due to phase mixing along the plane of the disk. So that goes as an exponential damping term, e to the minus e squared. And so what I'm showing here is jz sine theta z versus jz cos theta z, and it's color coded by this distribution function perturbation. Initially, we start from an n equals 1 and n equal to basically a dipole and a quadrupole. And since the stars near the center, that is the stars with lower actions, they're moving at larger frequencies than the ones away from the center or larger actions, we have this winding up that is due to differential rotation of the stars in this case. So we have a winding up of the spiral because of that, because of different frequencies of the stars. Now we go to a slightly more complicated model. Instead of a delta function in time, we have a potential that varies in time. So we just take a Gaussian pulse in this case. In this case as well, you have a winding term, which is going as theta z minus omega z times time, but there is also a factor which depends on the time scale of the perturbation and the length scale as well. And we have fading term and exponential damping term. There is a growth term as well. So basically the distribution function takes time to grow and then it decays due to phase mixing, as well as the vertical winding. And there is a mode strength term, which basically tells you what is the relative strength of these n modes. It goes as exponential minus n squared times this factor. So notice that this omega naught is basically 1 over the time period of the pulse. So for a fast pulse, your omega naught is large, and therefore this term is small. So you cannot really differentiate between the different modes. But for a slow pulse, your n equals 1 mode will actually dominate. So you will have more bending of the disk rather than the breathing mode that is n equals 2. Okay, so here what I'm showing is that for that Gaussian pulse, for different pulse durations, what does the winding look like? So from top left to bottom right, the pulse duration is actually increasing. So this is the fastest pulse, this is the slowest pulse. And you can see, hopefully, that the winding rate depends on the pulse durations. If you have a very fast pulse, the winding happens faster. For a slower pulse, the winding happens much slower. And the fading out of the perturbation due to phase mixing in the horizontal direction on the plane, that rate also depends on the duration of the pulse. For a fast pulse, the damping happens much faster, and for a slower pulse, it happens much slowly. So this tells us that we can put some constraints on the time scale of the perturbation or the pulse, given that we observe a snail with a certain winding rate and a certain fading rate. So now I've talked to you about the vertical phase mixing. That is what is giving rise to the snails in the action angle space in Z. But these perturbations are there also along the disk. So what about the phase mixing along the disk? So here what I'm plotting is the amplitude of that perturbation as a function of the wavelength for different times since the pulse reaches its maximum strength. So from blue to red, we have different times. And there are two things that I would like to highlight here. One is that the small-scale perturbations damp out much faster than the large scales. That's expected because it takes smaller time for the information to travel, or basically things get out of sync very quickly in the small scale. But in the large scale, it takes time for the stars to get out of sync. And the other curious thing is that for a given pulse duration, actually you can find some peaks at a particular wavelength. So the amplitude actually peaks around 10 kiloparsec scale. And so this model is basically predicting that for a pulse of a given pulse duration of a given time scale can actually give rise to a dominant wavelength of these perturbations along the disk. And we are predicting that it should be around 10 kiloparsec. And that can be understood from a simple argument of the time scales. That is, there are three different things happening here. So the perturbation grows with time, it decays due to phase mixing along the disk, and also there is a winding time of the perturbation due to vertical phase mixing. So these three time scales have been plotted here in different colors. And the important thing to note is that there is a trade-off between the time scales. When the horizontal phase mixing time is small, the other two are large, and vice versa. And these time scales actually match up right around 10 kiloparsec scale. So that again tells us something about the wavelength of the perturbation. So till now I have been showing you what happens for a single Gaussian pulse. But in that case, we saw that there can be some significant damping of the perturbation with time. And therefore, the idea is that, so how come we observe snails today that keep the damped out? There are two possible solutions. One of the solutions is that these snails are getting re-excited again and again by multiple pulses over time. And what can be the source of the perturbation? I'm going to come to that later. But basically what is being shown here is that instead of one pulse, you have several pulses hitting. So we have the first pulse coming in, it causes the spiral to wind, and then it kind of damps out a little bit, and then the second pulse comes in. And it basically keeps this going on for a long time. That's the idea of repeated excitation of these snails. So these are the basic predictions. We have a 100 mega-year perturbation time scale probably. And the phase mixing causes a fading of the perturbation. And so the snails are probably transient features. They're not going to stay there for a very long time. So we need a repeated excitation, which can be modeled by multiple Gaussian pulses in the simplest picture. So Elise is going to talk about this in more detail, but the source of the perturbation is probably something like a global bending of the disk, which is being excited by the passage of a massive perturber. So it's not probably Sagittarius directly causing the snails, but something it does to the disk, and the disk bends up and down, and that's probably leading to these snails later. And the wavelength of the perturbation is around 10 kiloparsec. So the future work is going to basically focus on this, that we get a slightly larger wavelength probably than what is expected. And that's probably because we are not taking into account the fact that these stars are doing epicyclic oscillation along the disk. And we also need to account for the shear due to the differential rotation of the disk. This was a simple model, but now Elise is going to move into a more complicated description that what happens in the general case with simulation.
Cool. Yeah. So as you heard from Uddipan, he was more focused on making predictions about what we would expect these spirals to look at based on a simple model, both throughout time and throughout the disk. My project was focused then on actually characterizing the spirals we do see in the simulations that Jason ran. And so you can think about a bunch of different metrics for trying to characterize a spiral in some small portion of the disk. So some of the metrics we looked at, so you can look at the mode of the spiral, so that's whether you see a one-armed or a two-armed spiral, the tightness of the spiral, so how wound it is, the initial angle of the spiral, so here's the pitch angle, and then as well as Uddipan talked about, the strength of the spiral, so whether or not you see a very strong spiral or one that has started to fade. And you could imagine other metrics or combinations of these metrics. So kind of the insight we came to very early on, talking to Catherine, was that we can unwind these spirals. So you imagine you have some spiral in action angle space. So as Uddipan showed, that spiral is just going to be given by a very simple equation. So you're just going to have some initial theta naught, which is the initial angle of your perturbation. And then that's going to wind up just according to whatever your frequency is times the time. So omega z t naught will then give you how far the spiral has wound since the initial interaction. And so you can basically, by translating to theta z omega z, you will end up with just straight lines. You can fit to these lines. That should give you your theta naught and your t naught for this spiral. Basically the same idea for n equals 2. You're now going to have lines that are separated by pi rather than 2 pi, but everything else holds. So this gives us some actual numbers for the different metrics I was talking about earlier. So you can have, again, the spiral mode, n equals 1 or 2. You can, in theory, have higher modes, but we really just focused on the first two. Tightness of the spiral, so that's just t naught, so your time since interaction. Pitch angle is going to be your theta naught, your initial offset. And in this simple model, we don't consider the strength of the spiral, but that's something I'll come back to. So we are making some assumptions here. So an assumption that we're in the short pulse limit. We expect to see both n equals 1 and n equals 2 modes, and that the spirals are not being re-excited. And that's how we can translate t naught to the initial interaction time rather than some re-excitation time. So how well does it work? So first you got to extract the spirals. Turns out that this is not as easy as it is to do by eye. But how we did this, so we started out by plotting our initial density, binned in jz theta z. You can estimate the background density by just randomizing in theta z. Subtract that off, identify remaining overdensity peaks. From that, you can then get your theta z's, your omega z's, and then just fit your line, both for an offset of 2 pi and for an offset of pi. And then we identified the dominant mode as just the fit with the lowest residual error. Cool. So once we built up all of the mechanisms to do this, you can then look at your spirals across the disk. So this is a look face on the disk for a single snapshot binned in J phi theta phi. And there are a bunch of different panels that are all just measuring the different things I've talked about. So down here, this is just the dominant mode. So you're going to have yellow is going to be an n equals 2 mode, and purple is going to be n equals 1. Up here, this is just log 10 of the interaction time. So this is just the slope of the line that you fit. Over here, that's theta naught. So that's just the intercept of the line modulated by 2 pi. And then lastly, in the bottom corner, I just have plotted the average VZ velocity. And so that kind of gives you an idea for what the motion, what motions are happening across the disk as we run through this simulation. And as we start to look through snapshots, you'll see that you can very clearly see the interaction with Sagittarius in that panel, and then that interaction start to spread out around the disk. Cool. So this is just for a single snapshot. You can already see that we see lots of structure in the different metrics that we're measuring, especially a very interesting structure in the dominant modes we see in different locations in the disk. But even more exciting was that we can then do this across time, so across a range of snapshots, and track the evolution of our spirals throughout the simulation. So I'm going to show a movie that tracks from about 2.4 to 3 gigayears, and this starts right after the first interaction with Sagittarius in the simulations. And you'll see that the strength and morphology of the spirals are going to vary across the disk throughout time. Cool. So here we go. So yeah, if you watch in the top right corner, you see the interaction with Sag start, and then patterns start to propagate across the disk. So these patterns will propagate both radially and azimuthally. You'll see that the spirals tend to be weaker in the center and stronger in the wings. So that's just set by the alpha value of the different pixels. The strength of the spirals tend to grow over time. And you also see the strong domination of these n=1 modes. And then for the interaction times, so that's the top left, that's log 10 of the interaction times. And you see we get interaction times of about 100 to 500 million years. So in line with what Uddipan predicted from his analytic model. Cool. Okay, so we can make these maps looking at the simulations throughout time, and then trying to figure out, okay, what are we actually seeing? What does this mean about how these spirals are formed, how they evolve? What does this mean about what we can expect to be able to learn about these interactions when we actually go and look at the real data that we have access to? So currently, we have some hypotheses about what's happening, and all of these require further testing, but fit with what we've seen so far. So as Uddipan was talking about, we think that the interaction with the satellite excites these global motion in the disk, and so you can kind of see this. This is just again a picture of all of the particles in the disk for the set of times that we were looking at. You can kind of see that this motion propagates across the disk. And as this global bending happens, you then form spirals. And if we look at snapshots, so the snapshots I was showing was right after the first interaction, but we've also looked at snapshots long after the first interaction, after the second interaction. And so we see that the spirals aren't really fading out. And so it seems like this global bending of the disk continues to re-excite these spirals. And so that creates these very strong spirals with short winding timescales. And this is interesting. It's a little bit of a bummer for our first hypothesis that, we should be able to track the interaction time by just looking at how wound these spirals are. But I think it also leaves like a wealth of room to continue to explore what's actually happening here, what is happening in the disk. So next steps that we're interested in looking at, so running perhaps a set of targeted simulations, so you just have a single passage of Sagittarius, shut that off, and then just let the disk evolve and see if this continued motion in the disk really is continuing to re-excite these spirals. Along with that, carefully tracking the motion of all of the individual particles, both in the disk and in the halo, to see if we can see this bending. And then, as Uddipan was talking about, expanding our analytic models, so having models that include radial epicyclic motion of stars, as well as shear. Cool. I think that's it. So yeah, huge thank you to everyone.
Yeah, that was amazing, both of you. So I think you almost said this, Elise, in your next steps, but I was just going to ask you both, do you think there's any hope of tying back from what we see in the data to an interaction time that happened with Sagittarius and kind of see if we can time those two, or is that kind of a lost cause now with what you've learned?
My feeling on it, and I don't know what Uddipan has to say, is that probably you can't tie that back exactly to an interaction time with Sagittarius, but I think that doesn't mean that there's nothing you can learn from this, right? I think you can learn more complicated things about how the disk is reacting to that interaction. And perhaps if we really continue to explore this and build models that we really trust, we could constrain like perhaps even more interesting things than just that by really studying this.
Yeah, I agree. So yes, so initially we thought that SAG alone can probably cause these snails, but then the time scales didn't quite work out that way. So we find like a few hundred million years probably for the pulse time scale, which is faster than the typical passage time of SAG. So that means that there is something.
Use your seat mic, please.
So that means that probably there's something else going on when we are hypothesizing that there is this global bending of the disk that is happening at a time scale which is nearly equal to the vertical oscillation time scale of the star. So that's a few hundred mega years. And that is what is probably causing these snails. But how does that connect to the initial passage of SAG? That is, I think we need to investigate that further in simulations with more targeted simulations, basically just having one single passage of SAG and then shutting that off, letting the disk bend up and down and see what that causes to the snails and things like that.
So this is great, really nice work. I think I missed the discussion or the reason why you get a wavelength of 10 kiloparsec.
Yeah, right. So, okay, so that's basically where naively I would expect that the perturbations to peak at a certain wavelength, because the perturbations grow and then they decay again due to phase mixing along the plane. I'm just talking about the amplitude of the perturbation. So I would expect that at certain wavelength, basically you have sort of a commensurability between your k sigma and n omega z. So that is similar to saying that your horizontal phase mixing time scale is matching up with the growing time scale. And that basically picks out a certain wavelength at which these perturbations will peak. So I guess that's the kind of hand-wavy argument that I can give you.
And going back to the simulations, like we do see, if you see like these strong, there is kind of a wavelength that we see. It's probably a little bit less than 10 kiloparsecs.
Right.
But
so we are probably over predicting a little bit. Maybe it's 5 kiloparsecs or something, because we are not taking into account. So we are assuming a uniform density along the plane. So that means that the stars can move at any velocities and can go as far out as possible. But in reality, that's not the case. So Martin and I just came up with this idea a few days back that probably we need to take into account this epicyclic motion of the stars along the guiding radius, so that the stars move out, but they have to come back again. So that means that the wavelength should decrease. It should not be as big as 10 kiloparsec, maybe a little less.
What would you expect for the wavelength given your model? What would be? What do you think it would be?
I would expect maybe a factor of 2 decrease, 3 or 4 kiloparsec, something. Yeah, shouldn't be smaller than that.
I hadn't seen the multiple times when you hit the multiple before, so I was struck by the fact that this spiral you didn't reset the spiral. The spiral stayed at the same phase. And that it's not what I would expect. I thought, yeah. So can you explain that?
Yeah.
You can ask them to go back a bunch of slides.
Okay. Right, so the first pulse comes, then it starts to fade away, and then the second pulse. So you're saying that it looks pretty similar, that the phase looks kind of
does reset. I think
yeah, it's resetting it a little bit. I mean, there's some growth, and then it winds, then it fades, and then growth, fades.
I guess I think of the interaction as shifting this. I'm thinking of ZVZ.
Right. This is in.
Yeah, which is, I guess, is equivalent.
Yeah.
So I think of it as a shifting, whereas this is doing a squash, which I suppose maybe, yeah.
Wait, so you,
In the one arm case.
yeah, maybe I didn't understand your question
No,
properly.
maybe I don't understand my question either, so that doesn't help. But I had another question. Do I get a second question?
Sure.
So intuitively, intuitively, right? When you have something interacting, your Gaussian model where you have the different lengths, and then you have the winding with different times, and you can probably show me in the equations. But my expectation would be intuitively, you have your pulse or whatever, and it gets longer, and during the interaction, that affects the winding time.
Yes.
But once the pulse goes away, surely it just goes back to the same winding.
So the pulse gets longer, you find that the winding time increases as well.
No, but I guess that what I'm saying is when you've got rid of the pulse, that's the perturbation. So why doesn't the winding time go back to?
Why is it winding at all? That's what you are asking?
No, shouldn't it wind faster so long as you go long enough? Shouldn't it just go back to the normal winding time? It's just during the pulse itself, right? Or am I missing something here?
I don't think it will wind faster because a very slow pulse means that you don't have anything, right? You really don't have any potential perturbation. So that basically means that things will change much slowly, or things will tend to change not at all. Like if you don't have any perturbation, right, you will just have this dipole or a quadrupole stay there, not winding at all. But you have a perturbation that is very slowly varying in time. That means that it'll start to wind the spiral maybe a little bit faster, and then you have a faster pulse, it starts to wind the spiral a little bit more fast. And for a very fast pulse, you will just find what you expect for a delta potential case. That you like, yeah. What is exactly your confusion?
Sorry. Just the one that once the pulse goes away, then you've just got the dynamics of the disk and its phase mixing. So then it should wind at the same rate.
Okay.
That's what I'm trying to say.
Okay, I see what it's.
And I'm surprised, but maybe.
That's possibly because we are ignoring the self-gravity of the disk here. If you take into account that, I think you will find phase mixing of the disk itself. In absence of any external perturbation, you will find that what you were probably talking about.
I guess what I'm trying. Okay. I mean, we should take this offline. We should take this offline.
Yeah, Rachel.
You can go back to Catherine's first question.
Do you understand my question?
I'm genuinely like, your pulse duration is half of your pulse.
Yes. In this case, it's basically
not on this one.
The total.
For the next one, where you have the pulse that's going, you have a comb. You have your Gaussian comb.
Yes.
Your interval is essentially twice the duration, right? Yes. So you're essentially just forcing it. And so did you do anything where you had that such that your interval is not a forcing mechanism of the pulse itself?
Okay, yeah. I had an overlapping pulse and the pulse that comes in much later. I tried that as well. So for an overlapping pulse, you will find some sort of curious interference between the pulse, the spiral due to the first pulse and the spiral due to the next pulse. It will not look similar as in this case. You just basically find that it keeps the spiral going on in nearly the same way. That won't happen if the pulses overlap. And if the pulses do not overlap at all, like instead of twice, if I have like a 5 times or 10 times, then you will just find that the spiral due to the first pulse comes, it winds and then fades, and then again the second one comes much later, it winds, fades, and that'll keep on going. You said that it's forcing the
same pattern because you are pulsing it at an interval that's
right.
So if you take your Gaussian, you push it all the way through, and then if you just had another one coming right back through, right? So
So the motivation was that I wanted to model the global bending of the disk, and since the disk is bending, basically the pulse time should be nearly an integral multiple, I guess, of the pulse duration, or nearly equal, because when the disk goes up, it has to come back down, and so there will be a coherence between these two time scales.
But if it would damp over time, couldn't you just then, like, I don't know, take a decreasing, like, did you do that maybe?
So a Gaussian pulse plus a damping?
Same interval, but maybe with slower duration. So you have, because that would kind of model maybe a damping of the.
Yes, I didn't do that. That's an interesting point. I will look into that. But I would assume that will just, that'll change the winding rate, maybe even make the winding rate slower as the pulse is decaying in amplitude.